Good morning from a virtual Berlin. This morning I'm going to be talking about debogonising 2A10/12. My name is Stephen and I'm going to be your host for the next 15 minutes. Although the V6 internet has been growing for many years now, the last rationalisation of the global unicast address space took place in 2006. No new unicast allocations happened between then and 2019 when, kinda like the buses, two of them arrived at once. One of them was issued to the RIPE NCC in June, one of them to Aben in November. This provides us with a couple of motivating questions. First, is it even possible to make use of this address space? It had been 12 years since the last /12s were allocated from IANA to the registries. It would be unsurprising if device configurations had baked those in and had been long forgotten about. We could have worked to clear those issues. Second, if it is possible to use this address space, is it safe to use this address space? Can we issue this to members? Is the space unused? Is it a target for an unusual number of attacks? Or is it already in use by a private network, given its adjacency to the prior RIPE NCC allocation? To give you a sense of scale, the 5 small boxes in the white region near the centre of the plot represent the /12s that were allocated to the registries back in 2006. These /12s have been covered in prior work. The merit study conducted in 2012 into 2013 looked at /12s from each of the registries. The traffic captured in this study is largely spillover or misconfiguration, given that these are covering prefixes, and you can see the distinction between the /12 at the bottom, which captured millions of packets in 5 days, versus the unused 13 and 14, which captured only 3,000 packets over the course of 3 months. Adding in the new address space, we have the opportunity to look at previously unused space, and to make it clear the size of the address space that we're looking at, it's that box there. This is an observational study. Our aim in running this study is to be as operationally useful for the communities that we serve as possible, and to that end, we were open and public in our experimental design. Initially, we announced the full /12 over BGP, and we followed up that announcement by announcing /32s and /48s drawn from that /12. Each of these prefixes is configured slightly differently to assist us or operators in debugging any particular issues, or to allow people to verify their routing security configurations. Within each of those prefixes, we set up one address responsive to echo requests. The aim with these was again to allow network operators to test their own reachability, but in addition we set up RIPE Atlas measurements to provide us with public measurements as part of the history of the initial announcement of this space. Finally, we captured all of the packet data sent into 2A10/12. Prior to our commencement, we announced our intent to conduct this study to network operator group mailing lists. We followed that up by announcing the /12 over BGP on January 13th. We then announced /32s and /48s over BGP on January 15th, and at the same time we set up the responsive addresses within those blocks. On January 16th, we publicised to the same network operator group lists that the study was now ongoing and precisely what the responsive targets were. And on January 20th, we tore everything down. In terms of the data that we collected, the Routing Information Service and, of course, route views will have collected the global routing state. The RIPE Atlas measurement data is, of course, public, and links to the measurement results are in the paper itself. And finally, we analysed the traffic that was captured by 2A10/12. This is the part of the study which cannot be fully public because it's packet data. And so in the paper, we spend a lot of time focusing on this part. Our intent is to find a means by which we can share more of this, but we're not quite there yet. So let's look at the traffic that we captured. Over the course of the week, we captured a little over 85 million packets arriving at 2A10/12. That's a little bit of a cheat because 78.7 million of those were generated by the RIPE Atlas measurement platform. But we can isolate those and remove them from the analysis. The full captured dataset looks a little bit like this, with 5.8 million TCP packets, 132,000 UDP packets and 79.3 million ICMP packets. Now that ICMP traffic includes the traffic generated by RIPE Atlas measurements, which we can remove. And then the remainder looks a bit like this, with around about 580,000 ICMP packets. That ICMP traffic will include the echo requests solicited to the 8 responsive target addresses. If we take a look at the 5.8 million TCP segments, and we view them as a time series with packets per minute on the y-axis, we can see that the vast majority of the 5.8 million packets that we captured arrive in 2 short bursts near the start of the study prior to the /32s and the /48s being announced. This traffic has some very distinct characteristics, none of it especially crazy, but simply consistent. So all of it contains a consistent source port of 49152, consistent destination port of port 80, no data in the segment, and the SYN flag set as if something is trying to pop open a connection. It all contains an oversized MSS value as if the host is configured for an IPv4 network, and the key defining characteristic is that each target is targeted multiple times, and for each subsequent packet, the hop limit increases. So this appears to be sources that are attempting to do trace routes into this network address space. It seems likely, given how rapidly these packets arrived, that this is an automated process that simply watches BGP from US space, and it kickstarted a measurement. These measurements were coordinated across more than one ASN, with what would appear to be one network which specializes in network intelligence operating the show. This is fairly innocuous, although of course we don't know what the measurement platform would do if something actually picked up the connection. If we refocus the graph to look instead at the rest of the traffic that's down there at the bottom, we can see that there is some additional noise throughout the rest of the study. If we isolate some of that traffic, we identify 160,000 TCP segments with the following characteristics, whereby this subset of traffic arrives from 2 origin IPs located within 1/64 NAS 58461, that's China Telecom. All of these packets have the SYN flag set with no data payload. They're all targeting addresses within 3/96s. They are targeting various common TCP ports such as 6379 for Redis, 6697 for IRC, or low number ports such as HTTPS, POP3, IMAP, etc. And they also, like the TCP traceroute covered already, contain an oversized MSS value. This again indicates a software stack or a network platform that's configured for an IPv4 world. There is an additional 41,000 TCP segments that have a destination port 443 and the ACK flag set and what appears to be an encrypted payload that are targeting various destination IPs. It is not clear if that is traffic that's trying to solicit a reset response or if it is legitimate backscatter from some other network. We haven't investigated that far. Beyond that point, there is a ever-diminishing set of what appears to be noise, including packets with junk source addresses and Christmas tree packets, etc. If we take a look at the 132,000 UDP packets, what we see is inter-arrival rates that are much more spread out through the week. This is traffic that is not dominated by any one particular time period like the TCP traffic. And around about 50% of the traffic that we collected is DNS. The majority of the DNS was a misconfiguration in one network, where we contacted the host, and they, as far as we know, have corrected the problem. In the remaining DNS traffic, around 6.7 thousand queries appear to be intended for abuse.net. Another 500 are querying for the version.bind string. There are a few queries for A and quad A records, but there's nothing especially outlandish or onerous here. A lot of the remaining UDP traffic is basically filled with noise. There are only a couple standouts that are worth mentioning, including 10,000 that appear to target port 1, and another 1.5 thousand that appear to have origin port 443 and look like they're carrying an encrypted payload, but nothing that really sticks out. Finally, if we look at the 580,000 ICMP packets that we collect, these are dominated by the network operators sending pings to the addresses that we solicited. You can see in the time series when the traffic picks up. This is not the most exciting part of the dataset, but it does tell us that 892 separate /64s did send echo requests into this network. The remainder of the ICMP traffic is very small. It's only 27,000 packets and includes a lot of junk, including traffic that's sent from nonsense IP addresses or includes incorrect ICMP types or codes. So the full dataset looks something like that. We captured 85 million packets, 78.7 million of them were generated by RIPE Atlas, so we kind of throw them away. And the remaining 6.5 million falls into a few main categories, including TCP traceroute, some TCP port scanning, a bunch of misconfigured DNS, and a lot of echo requests that were solicited. In the paper, we use RIS to take a look at the routing system, and the key question for us here is, are these prefixes visible? And the short answer is that yes, they are visible at all 21 route collectors, and if that wasn't the case, then we would have a bigger problem that we would need to solve. From there, the next question is, how widely visible are the prefixes? We didn't particularly stop to study the AS paths, but we did look at the number of RIS peers that are propagating the prefixes back to us. We compare these prefixes against a stable anchor prefix, which has been announced from the same origin for many years. In this graph, what I'm showing is the number of peers that are propagating each of the announcements, and the uppermost line is the number of peers propagating the stable anchor. That's around about 270 plus or minus 1. The lower line is the /12, which is fine because a /12 is an atypical prefix length that you wouldn't expect to see in the routing system, and there is no route object. So it's quite reasonable for people to not propagate that one. In fact, maybe fewer people should be propagating that one. The cluster of lines in the middle is all of the /32s and 48s, and I can hone in on those to show an indicative pattern, and that is that the 4 prefixes that have routes in the route database, that's the prefixes that have the numbers 4 and 6 in them, are the ones that are visible via most peers, which is good and expected, and the prefixes that do not are the prefixes that are slightly less visible, and that's fine. What we additionally see is that when all of the announcements are withdrawn, the path hunting phase kicks in, and in that process, while things are being shaken around, we do additionally identify new peers which could have forwarded the announcements themselves, which suggests that there is some scope for people to remove filters and or that the anchor prefix simply has had a longer time to identify those slightly less used paths. Finally, we looked at the collected RIPE Atlas measurement data, and our broad goal in doing this was to understand what the reachability to the test targets actually looked like. In aggregate terms, we see a clear pattern. So what we have is around 95% reachability to 6 of the target addresses. And then we see a distinctly lower 88% reachability to the 2 target addresses that have neither the route object nor the RPKI ROA. All of these are lower than the reachability to the equivalent target address inside the anchor prefix, where we see a reachability from the Atlas platform of around 99%. So we wanted to dig in a little further and understand how widespread that was and what the patterns were. We observed 2 main patterns across the probes. The first is there is a set of probes that receive no response from any of the test addresses at any point during the study, and we see these across 39 ASNs. Now, remember that an ASN can host many more than one probe, which is why the impact can be so noticeable. But in these cases, generally, we collect the ICMP echo request in the packet capture, but the probe itself didn't receive a response, which suggests that there is filtering happening on the reverse path. The other pattern that we saw is there exists a set of probes where we have no response from the 2 target addresses that have neither the route object nor the RPKI ROA. And we observe those primarily in AS3320, that's Deutsche Telekom, or ASNs that route via 3320. And in those cases, we don't collect the ICMP echo requests in the packet capture, implying that the route is simply filtered at the network itself. If we disregard these 2 categories, the response rates that we left with to the test targets are much closer to the response rates that we observe to the equivalent target in the anchor prefix, i.e. we see around about 99% responsiveness, and that's from a broad set of probes. We see that from around about 3,600 probes located across 1,300 networks. That is a representative set of the IPv6 enabled Atlas probes that are out there today, and that is a good result. In summary, this paper has presented our work around the debogonisation of the first new/12 to be issued to a registry in around 12 years. We've presented our work looking into the background noise that arrived in this address space during 1 week of announcements, and what we determine is that the traffic collected in this space is not problematic. We see no obvious evidence of private networks using this space, and the traffic that we collect is not concentrated on any particular subnet. Further, routing visibility is generally good, especially for this being fresh space that nobody has ever used before, and reachability is also generally good, with a couple cases that we were able to analyse and understand. Finally, questions. I am happy to take questions over all of the various means that we have available to us, and I will do my best to answer them. Thank you very much for your attention.